All right, today we're going to talk about heaps. Why isn't this one like the other one? That is a great question.
You didn't take it from them?
Yeah, I totally stole this off the internet.
You did take it from the same people.
No, I did not take it from the same people.
Good.
Oh, then the book?
Yes.
Yeah.
That's what
Yeah. Oh, well, you're welcome.
I found the binary tree that the book had all, like, that it had all messed up.
Mhm.
I found it in the next book.
Does it work any better?
No.
Okay. All right, so heaps. Heaps and heap sort. Heaps are one of these, let's see, data structures that's not used too often, but but it fulfills a niche extremely well. There's certain parts when you're programming where a heap just does beautifully, and then of course not helpful really after that. But we'll talk about heaps, which are actually a pretty important data structure, and then heap sort, which hopefully you can detect that you use a heap in order to sort something.
Sure.
All right, so heap sort.
Oh, we have animations.
You don't like the animations? Yeah, neither do I.
I don't like the font.
You don't like the font? Okay. Any other complaints?
I just
I like
hate
the
it.
The
The
color.
color's not good.
The color's not good. Okay.
It's very distracting.
Any others? You got to get them all out right now.
I don't understand the three, like the blue dots on the side. That doesn't make sense.
Oh, well, there's a fourth one down there.
Yeah, it's okay.
Okay.
That shouldn't be there.
Any other complaints? Jamie, come on. Okay,
Yeah, I don't like the font either.
You don't like the font either? Okay. Well, that's nice. So, it is a well-known traditional algorithm. Luckily, it's always in log n. Quicksort's usually in log n, but in the worst case, it's in squared. Quicksort is generally faster, but heap sort is actually better for critical time applications because it's more predictable and how long it's going to take in order to sort something. All right. What is a heap? Definition of a heap. Okay, we're going to talk about heaps. Oh, there's two definitions. What's the first definition that we know of? It's this one, which is a memory. All right, now everything's going to get confusing
Oh gosh.
because there's heap, the memory, and then there's heap, the data structure. A balanced, left justified binary tree in which no node has a value greater than the value of its parent. All right, first off, it is a binary tree. It is not a binary search tree, so it is not going to look like this right here. This is not a heap at all, okay? But it's going to look like a binary tree. It's just going to be ordered a little differently. What are you talking about?
It's gonna be like that one.
Yeah, this one over here, except for this is not left justified. You'd have to
What
put,
about that?
what?
That thing.
This saying, this is not a heap at all. This will never happen in a heap. Actually, this would never happen in a heap either. It would have to have a node right here because it's always going to be full and left justified. And I'll show you in a moment. The two definitions have almost nothing in common.
Just the same name.
So just the exact same name. I will try and say heap for the memory and binary heap for the data structure, but keep in mind that I'm not going to always be able to do that. Heap sort, of course, uses the data structure, a binary heap, not, well, technically it does use heap memory, but it doesn't have to. All right, balanced binary trees, so, wow, come on, stop this. All right. The depth of a node is distance from a root. Notice that this is balanced. A binary tree n is balanced if all the nodes have depths 0 through n minus 2, so to speak, in this one. Or have two children. This is also balanced. This is not balanced. Why is this last one not balanced?
Because it has two things that aren't full.
Right. There's nothing full right here. There's nothing. There should be a spot here. I can move that guy up there or something. Okay. Left justified means that all the nodes on the final level, where you may have something empty, are all moved all the way to the left, so to speak. So that's left justified. All the leaves are the same depth. All the leaves that are to the left of the nodes, right. So this is not left justified because they're not to the left, right. Like this node should be over here, this guy could be over there, and then it would finally be left justified. All right, any questions so far? Because I just ran through that real fast. Talked a little bit about balanced. I think the pictures help. So balanced, balanced, because again, just the last level is the only one that doesn't have any nodes. Welcome back. And then not balanced because there's more than just the last level that doesn't have a node in it. And left justified, on that final level, everything's moved to the left, so to speak. So everything's on the left, but you have some holes right there. All right, so first off, we'll learn how to turn a binary tree into a heap, because I told you it is a binary tree. It's a little different. And then how to turn a binary tree back into a heap. Into a heap after it's been changed a certain way. Okay, sure. And finally, this cool part, we'll see how we can use the ideas to sort an array. Sure, this is an awesome part. Actually, once you understand how a heap works, the sort is really, really easy. All right, first off, the heap property. Now, with the binary search tree, when you're looking up here, you had a property where each node, for this one, everything to the left had to be less than, everything to the right had to be greater than. Okay? So the heap property is going to be a little different. Now the heap property can change, so to speak, as long as you maintain it down the line. I mean, you could have this be reversed in a binary search tree where everything to the left is greater and everything to the right is less than. I mean, that's confusing, but you could do it that way and it'd still be a binary search tree as long as you coded it. So the heap property is going to be similarly where each node is going to have a special property in relation to its other nodes. And let me make sure I stay with the slides. I believe they say greater than. If the value in the node is as large or larger than the values of its children. Okay? So, the blue node has the heap property because 12 is greater than both 8 and 3. All right? So the parent is always going to be greater than its children. Blue node still has a heap property because it's equal to, but now it no longer has the heap property. How could we change the last one so it would have the heap property? Yeah, switch the 14 and the 12. Everyone tracking? All right, sure. Of course, all leaf nodes automatically have the heap property since they don't have any children. They're automatically satisfy the property. A binary tree is a heap if all the nodes in it have the heap property. All right. The slides are going to go through some examples, but let's do some on the board once I find the eraser.
That's the glare.
It's really weird looking at the screen trying to do this. All right. Okay.
I can't really read it now.
You can't read that? I'm sorry.
Where are we glare today?
All the comments in this class. All right. Give me a number.
We're trying to not die inside right now.
Give me a large number.
536.
9,000.
9,000.
There
That
we
is
go.
what we're doing.
What about over 9,000?
What was the next one? 536?
Yeah.
All right. Can it go on the left or the right?
Either.
Either. All right, keep that in mind. It can go on either side. Give me another number.
2.
Something a little larger than 2.
739.
739. All right. How about another? Huh?
What are you gonna see, Sanjay?
Any other numbers?
1, 2, 3.
1, 2, 3. Where could 1, 2, 3 go?
Anywhere.
To the left.
Anywhere.
Doesn't have
Put
to
it
be
right here.
Why the right?
Because I felt like putting it there.
Just go on the left if it's less than.
No, it doesn't
No,
matter.
we're satisfying the heap property. Now this is technically still not a heap, but that's okay. Give me another number.
3, 2, 1.
3, 2, 1.
4, 5, 6.
4, 5, 6. I'm gonna.
7, 8, 9.
That one's not gonna fit. Let's do 6, 8, 6.
I'm supposed to say
686 after 586 before the 786. Okay, that's also a heap because each node is larger than its children. 9,000 is bigger than those two, 739 is bigger than those two, 536 is bigger than those two. Okay. All right. Everyone see what we did here?
So it doesn't matter that the 686 is larger than the 536 because they're not the same parents.
Right. Yeah. Okay. So yeah, there's really no order. Well, I'm sorry. There is an ordering, but it's not a strict ordering like you're used to in a binary search tree. It's still a binary tree, but the order is a heap ordering, or a binary heap ordering. If that helps any. All right, let's look at some slides. Okay.
I don't like that starts with lowercase.
What, sift up?
Yeah.
Why would not start with?
Title of the slide.
But if you're using camel case in your code, you always start with a lowercase s.
This is just a
Slide
presentation.
title.
What?
This is just a presentation note.
It's not the code.
All right. All right. This is your new homework. I want you to go online, find these slides, email the author, tell him to change it, and then tell him to email me the update of the slides so I can use them. All right.
How much is this worth?
How much it's worth to you to not have a capital letter.
Yeah.
What?
She said a project grade.
All right, so sifting a node up. So the blue node does not have the heap property. Wow, really? Now the blue node has its heap property. Wow, okay, really. So we're just sifting something up. Okay, that's amazing. This is sometimes called sifting up. Well, what else is it called? Notice that the child may have lost the heap property. Okay, let's do this example on the board. Give me another number.
789.
789. All right. When you add a heap, you always add over here, basically to the next position, furthest to the left. Does this have the heap property now?
No.
No. What do we need to do? Well, we need to what?
Sift it up.
Let's sift it up. So 789, 3, 2, 1. 789, 3, 2, 1. Do we have the heap property?
No.
No. Gotta sift it up. Wow. I just have to change one digit. Isn't that nice? 789, 73. Do we have the sift property? We're done. All right. Give me another number.
9001.
9001. Of course you would make me do this.
Yep.
Wow. Does that have the heap property? No. I'm gonna put 9001 up here in case I forget.
Should have done 9,000.1.
Do we have the heap property?
No.
Yep. Let's sift up. Do I have the heap property?
No.
Let's sift up.
Oh, you cheated.
Do I have the heap property?
Yes.
All right. What's the runtime complexity of sifting up?
And log in? Or log in?
One of those.
I want to know where you got in login from.
You're not doing the whole tree.
Right.
You're dividing it in half.
Right.
Log.
Log of n. Right, because how many levels are there in the tree? Log of n. So worst case, you're doing a log of n sifts. Okay? So
Best case, you're doing one.
or none. Because it just, I can put a 1 right here next to 686 and we're done. Okay. We're going to construct a heap. Okay. A tree consisting of single nodes automatically a heap. Well, that's nice. We add by one node at a time. Add node just to the right of the rightmost node in the deepest level of its full start new level. Okay. So example, we have this. Add new node here, and then add new node here. Okay, you'll see the ordering of how we add nodes conceptually.
To the left.
To the left, yes, to the left. Oh my goodness. So each time we add a node, we may destroy the heap property. To fix it, we sift up. Each time we sift up, the value of the topmost node may increase, and this may destroy the heap property of its parent. So we keep repeating, moving up the tree until we don't need a swap or we're done. Basically, what I just showed you up on the screen. We reach the root. Because once you reach the root, you're done. So we have an 8. We can add a 10. We need to swap that, which becomes a 10 and an 8. Then you add a 5, so we're good. We add a 12. Do we need to do anything with that 12?
Yes.
What are we swapping with?
8.
All right. Do we need to do anything? Okay. What?
Can we code it now?
Maybe. Well, we haven't got. How would you store this?
As a tree.
As a tree. Well, hang on. We'll hopefully get to the coolest part of a heap.
As an array.
How could we? Why would we store this as an array?
Because you mentioned arrays earlier.
Good. Notice that the other children aren't affected. The 8 is not affected because the parent gets larger, not smaller, so it's okay. And then we can keep sifting up because, again, the 5 is not affected because the 12 just got larger. So you understand why the heap property is okay? You just keep sifting up and you're okay? All right. So here's another example after it's been heapified.
That's not a word.
Oh,
Is that in the dictionary?
it is in the STL. The C++ literally has a function called heapify.
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 Better than Spotify.
Better than, that's what it should say right when it does it.
That'd be a good band name. Heapify.
Heapify?
Yeah.
Huh. Okay. Maybe we could start a band here, our data structures band.
I don't know.
Can we code everything in JavaScript?
Why are you so negative today?
If we start it, can we get an A in the class?
If you sing about all these data structures correctly, then then you will have proven to me you understand them.
That sounds like Travis E.
Travis?
I'm a music minor, so.
Yeah, okay.
He's got it.
Of course, you have to do
Does,
some
like,
composition.
crappy, like, music parody videos.
Oh, I love parody videos.
Ain't nobody got time for that.
Yeah, that's what I thought would happen.
Especially with this class.
Again, notice heapify does not mean sorted. Is this heap sorted?
No.
No. Keep that in your mind. It is not sorted. You are just satisfying a heap property that you came up with. Doesn't change the shape of my binary tree. It's still balanced and left justified because it started out that way, sure. Removing the root. Hey, that's kind of cool.
What?
We have a stray arrow. Suppose we discarded the root.
They're missing the root.
Well, yeah, we got rid of it.
That's sad.
Well, let's do that on the board first, because I think it's a lot more fun. So let's get rid of the root.
Oh, and then
It's gone. It gone. All right, first rule is you take the last node in the tree, a 7. That's just part of how this works, 739, you put it up here. Now, do we have a heap?
No.
No. So, previously we sifted up. This time we're going to sift.
down.
Whoa! Oh man, you were on the top of it. All right. Which way should we sift down?
Towards the knocked out.
Why?
Because that one's greater than the 739.
Yes, right. You always sift towards the larger. So we're going to take this 90,000, put it up here. 739. Do we have the heap property?
No.
What do we do now?
Which is 789.
789. Do we have the heap property?
Yeah.
So we're done. What is the runtime complexity of this?
And log it.
Okay.
Log in. Just straight up log in. All right, so deleting the top node and then reheapifying is log in. What is the top node? It is always, it's always the root. But in this example, what is the top node always have to be?
The maximum.
The maximum. So when you remove from the heap, and the heap property is your parent is always larger than your children, you will always be removing the highest node, the largest node, whenever you remove. Keep that in the back of your mind.
You need a function that finds the maximum.
Hmm?
So if you need a function that finds the maximum.
Well, if you just store everything as a heap, then your max is always the first element, your root. All right, so we got rid of the root. How do we fix it? Well, move the rightmost node to the new root so that 11 up there, there it went. And then, of course, it's not going to be happy. So what do we do?
Sit down.
So what are we replacing the 11 with, or swapping?
22.
The 22. Why could we not use the 17?
Because the 17, because 22 is bigger than 17.
Right, so you need to use the largest one. We can sift up the root. I prefer sift down. You gotta be kidding. Sift down. There you go. Are we good?
Oh,
What are we swapping now?
22.
All right. Whee. Are we done?
No,
Which one do we do now?
21.
Whee. Are we done?
Sure.
Yes. All right, so now we're done because the tree, every node has or maintains the heap property, the binary heap property. Again, the largest or a largest value is in the root. So always keep that in mind. We can repeat this process until the tree becomes empty, constantly removing.
Why is it or a largest?
Well, if you have two 22s, this 22 is not the largest. It just happens to be a largest because both of those are
So the same
largest.
value.
Yeah.
What if you had a tree of all the same value?
Well, that'd be easy to maintain. Maybe that should be your solution to the world. All binary trees must contain the same value. That's an interesting solution.
I would like that.
It's not useful. This produces
Yeah, I know.
That's all.
this produces a sequence of values in order from largest to smallest. What is it? What? How, wait, how?
What?
What? How? What even is?
Where are largest and smallest? What?
Well, what do we do?
Put the largest to the top.
We remove the top, which is the largest. All right. Then we shift it down. And now, if we want to remove, we would have the. If we remove from the root, what's the root containing?
Largest?
The largest. So we removed once, we got the largest value. If we remove the second time, we get the second largest. If we remove a third time, we're going to get the.
Third largest.
If we remove the fourth time, we're going to get the.
Fourth.
What does that sound like?
N times.
Yeah, we do it n times, and then
You reheap n times however many nodes are within the tree itself.
right. So what's this starting to sound like?
O to the n.
In login?
In log n to do what?
Find it from largest to smallest.
Yeah.
To get not find. Well, yeah, find from largest smallest,
Put
which
it
is
into an
Sort.
array.
which is a sort.
I get it.
Now I get it. Now I maybe.
So that's just a way of doing sorting. All right, now that I've explained everything, let's at least start getting some details in. Actually, let's do that on the board. So we got 9,001. I already showed that the first time, right?
Yes.
All right, so we're going to remove the next one, which is 9,000. And then we're going to remove the one all the way to the left at the end. 3, 2, 1, put it up here. Is that a heap?
Nope.
So where do we swap with?
The 7,
7, 8, 9. What do I swap with?
the one on the left.
The one on the left.
So I couldn't see what it was.
That one over there.
That one.
Are we done?
Yeah.
Yes.
All right, so let's remove the largest, which is
7,
7, 9.
9.
And then we got to put the 6, 8, 6. Oh, no, not the 6. Yeah, 6, 8, No, that's not right. Hold on.
Was it say would you do 1, 2, 3?
1, 2, 3. Thank you. That was close.
You're missing your cell phone.
I am. All right, what do I swap with?
739.
739. Any more swaps?
Yeah, 686.
Are we done?
Yes.
All right, I'll remove the largest. What goes up here?
450.
456.
Oh, sorry.
It's okay. Sight. All right. What do I swap?
Yes.
Yes.
What do I swap with?
686.
Am I done?
Yes.
All right. Remove the root again. Put the 1, 2, 3 up there. Do I need a swap?
Yes.
Who am I swapping with?
536.
All right. Am I done?
Yes.
All right. Who am I putting up here in the 536? 3, 2, 1. Do I need a swap?
Yeah.
What?
56.
456. Am I done? What?
Yes.
Yeah, all right. What do I put up here? 1, 2, 3. Do I swap?
Yes.
Am I done? Oops. 3, 2, 1. That guy. Put the 1, 2, 3 up there. And I don't need to swap because he's done, so there's 1, 2, 3. Are those sorted?
Yep.
All right. Any questions about that? All right.
How do we code that?
Carefully. All right. Because the binary tree is balanced and left justified, it can be represented as an array. Our operations on binary trees can be represented as operations on arrays. To sort, heapify the array. While the array is an empty, remove and replace the root, reheap the new node. That's just what we did. So mapping it to an array. Okay, how do we take this structure and put it in an array?
Do that.
Huh?
Do that.
No, because that's no longer a heap.
Oh.
That's a sorted array.
Could we, as we took off the root,
Here we go.
could we put it in
The screen just did it. Wow, these index values are not aligned correctly.
That is annoying.
That is super annoying. Well, anyways, nodes 0, 25, then you get 22 to 17, 22, 17, 19, 22, 14, 15, yep, 19, 22, 14, 15, then 18, 14, 21, 3, 9, 11, 18, 14, 21, 3, 9, 11. Y'all see that ordering?
It's just going across the rows.
You got it, going across by the rows. Notice, the left child of an index is at index 2 times I plus 1.
Sure.
Okay. Well, if we're at 0, and we want the left child, 2 times 0 is 0, plus 1 is 1, the 22, boom. If we're at 1, 2 times 1 is 2, plus 1 should be 3, 19. And we're at position 3. 3 times 2 is 6, plus 1 is 7, so that should be 18, 18. Okay? Let's look at that 14. 14 is at index 5. 5 times 2 is 10, plus 1 is 11, should be 9, which index 11 to 9. Okay? The right child's at 2 times I plus 2. 25, 0. 2 times 0 is 0, plus 2 is 2. 17, 2. Let's go with the 17. Sure, 17 is at 2. 2 times 2 is 4, plus 2 is 6, so that's 15. 15 is at 6. Let's go with that 14 again, which was at index 8. 14. That 14, because there's another 14 over there. This 14 is at index 5. That makes more sense. 2 times 5 is 10, plus 1 is 11, or plus 2 is 12. Wow, that was bad. So index 12 is the 11. Okay? So you can quickly calculate where their left children and their right children are with this calculation. Isn't that nice?
Yeah.
Kinda.
Maybe.
Maybe.
Want to give us an example?
Yeah. The children of node 3, so that's the 19, are 7, because you're at 19, so it'd be 7 and 8, which are 18 and 14. Hopefully myself speaking is clearer than these slides.
Yes.
I thought so. The root is the first element of the array. The rightmost node of the deepest is the last element. So you swap them. Literally, when you do a remove, you pass back that 25, and then you move the 11 and the 25 to each other, and then you decrease the size of the array. It's not doing it for me. Okay, that's nice. Basically, when you remove the root, notice the root was 25, you swap them with the last one, because you're going to move the 11 up to the root, right?
Yeah.
And then you decrease the size of the array. It's no longer 13, it's now 12. So you just have your size cut off right there.
So it just cuts off that last value.
Yeah, you got it. Because that's how you delete from an array.
Sure. Snip, snip.
Now you need to reheap, because obviously the 11 is not larger than its children, 22 and 17. Okay, so it just reheaps it for you. That's nice. Instead of doing it one by one, great. And then it will have to do it again. If you want to get the next largest, you're going to remove that 22 because he's at the top, and then you swap with the n and decrease the size.
Are they actually like cutting that off, or are they just like leaving it there?
They're cutting it off because this is actually going to show you something. What's pretty cool about the way it's doing this? If you kept removing the root, what would you have when you're done?
An array from smallest to largest.
Which is
Sorted.
sorted, right. So that's why they were swapping them like that. All right. And the array is sorted. So heapifying the array. How long does it take to heapify an array?
Again.
In login, right?
In login. Why?
Because you have to.
You have to add each element, so that's in. And each time you add an element, you have the chance of sifting up, which has a runtime complexity of log in. So it's in log in to heapify the array. Sift it up, pause. So it's log of n, therefore it's in log in. While the array isn't empty, remove and replace the root, reheap the new node. We do this while loop n times. Yeah, because removing and replacing the node takes O of 1, and then the total time is n times however long it takes to reheap the method, and reheap goes down. That's that sifting down. Wow, this is really long. So the path is log n. So the reheaping takes log n, which means that to reheap, to remove from n times takes n log n. So that means our total time is n log n plus n log n. The while loop takes n log n, so the total time is n log n plus n log n, which is n log n. The end.
The end.
The end.
The end. All right, any questions conceptually before we go to coding this? No? All right.